Black holes are cosmic enigmas that defy the laws of physics as we know them, swallowing everything that dares to come too close, even light. They are born from the collapse of massive stars, their power and complexity stretching far beyond what we can currently understand. What truly lies inside a black hole? Is it a void of endless nothingness? Or could it be a gateway to something extraordinary? From their immense gravitational pull to the theoretical realms of wormholes and quantum secrets, black holes offer a glimpse into the exciting unknown. Let's explore the science and speculation surrounding black holes, peeling back the layers of what we know and diving into the mysteries that remain unsolved. The event horizon, where the known universe ends. The event horizon represents a boundary, a place where the known laws of physics are pushed to their limits. Surrounding every black hole, the event horizon is often referred to as the point of no return. This is because once something crosses this invisible line, it is impossible for it to escape. Escape velocity is the speed an object needs to reach to break free from the gravitational pull of another object. For instance, on Earth, a rocket must travel at least 11 kilometers per second to escape the planet's gravity. The stronger the gravity of an object, the higher the escape velocity becomes. In the case of black holes, their gravity is so intense that the escape velocity exceeds the speed of light, around 300,000 kilometers per second. Since nothing can travel faster than light, nothing can escape the event horizon. The event horizon is not a physical surface. It doesn't have a solid structure like the surface of a planet or a star. Instead, it's a theoretical boundary. If you were to hover just outside it, you might not even realize how close you were to the edge of one of the most extreme phenomena in the universe. However, the moment you pass through it, escape becomes impossible. This is not because of any visible barrier, but because the warping of spacetime caused by the black hole's immense gravity becomes too extreme. Once inside, all paths, no matter which direction you try to move, lead toward the center of the black hole. On one hand, the event horizon is the threshold that defines the black hole. Without the event horizon, there would be no way to distinguish a black hole from other dense objects in the universe. On the other hand, the event horizon conceals what lies within. The singularity at the center of a black hole, where gravity becomes infinite and space-time curves infinitely, is hidden behind the event horizon. No information can escape from this region, meaning that scientists cannot observe or study it directly. This shroud of secrecy makes the event horizon a tantalizing boundary between what we can observe and what remains unknowable. From a distance, an outside observer would see an object approaching the event horizon slow down as it gets closer. This effect, called time dilation, happens because the black hole's intense gravity stretches time. To the distant observer, the object would appear to freeze in place and grow dimmer as the light it emits becomes increasingly redshifted, eventually fading from view. However, for the object itself, time would seem to flow normally, and it would pass through the event horizon without noticing anything unusual at that exact moment. The size of an event horizon depends on the mass of the black hole it surrounds. A stellar mass black hole, formed from the collapse of a massive star, might have an event horizon just a few kilometers across. In contrast, supermassive black holes, found at the centers of galaxies, can have event horizons spanning millions or even billions of kilometers. When material, such as gas or dust, gets too close to the event horizon, it can be drawn in by the black hole's gravity. Before crossing the event horizon, this material often forms a spinning disk around the black hole, known as an accretion disk. As the material in the disk spirals inward, it heats up and emits intense radiation, making the region around the black hole one of the brightest in the universe. However, once the material crosses the event horizon, it vanishes from view, adding to the black hole's mass. According to quantum mechanics, information about the state of particles should never be lost. However, anything that falls into a black hole seems to disappear completely once it crosses the event horizon. This apparent loss of information challenges some of the most fundamental principles of physics and is called the information paradox. Scientists are still working to resolve this paradox, and it remains one of the biggest questions in theoretical physics. Inside the Schwarzschild radius, a one-way ticket to the unknown. The Schwarzschild radius is the distance from the singularity, the core of the black hole, to the event horizon. Named after Carl Schwarzschild, the physicist who first solved Einstein's equations to describe a black hole, this radius is key to understanding the geometry of spacetime around these enigmatic objects. At the Schwarzschild radius, the curvature of spacetime reaches a critical point. Gravity is so strong that the escape velocity matches the speed of light. This means that for anything within this distance, matter or energy, there is no trajectory that leads outward. All paths, no matter how they begin, inevitably curve inward toward the singularity. To visualize the Schwarzschild radius, imagine spacetime as a stretched rubber sheet. A black hole is like a heavy object placed in the center of the sheet, creating a deep, steep well. The event horizon marks the edge of this well, where the slope becomes so steep that nothing can climb out. Inside this radius, the fabric of spacetime is so warped that all directions lead downward toward the singularity. Outside the event horizon, spacetime is still warped by the black hole's gravity, but it is possible to orbit the black hole or even escape its pull if you have enough energy. However, as you approach the Schwarzschild radius, the warping becomes more extreme. Time and space begin to behave in ways that defy our normal understanding. Time slows down for an object nearing the event horizon, as seen by a distant observer. Space, meanwhile, seems to stretch infinitely in the direction of the black hole. Crossing the Schwarzschild radius marks a fundamental shift. For an object inside this radius, the flow of spacetime is so distorted that the roles of time and space effectively switch. Outside the event horizon, you can choose your direction in space. You can move forward, backward, left, or right. Inside, however, the direction of time is aligned with the pull of the singularity. Just as you cannot stop moving forward in time in the everyday world, you cannot stop moving toward the singularity once inside the Schwarzschild radius. It becomes a one-way journey. The area near the Schwarzschild radius is a place of extreme physical conditions. As material approaches the event horizon, it is stretched and compressed by tidal forces caused by the black hole's gravity. These forces are more pronounced for smaller black holes, where the curvature of spacetime changes more rapidly. For larger black holes, the tidal forces near the event horizon are less severe, allowing objects to cross the Schwarzschild radius with relatively little disruption. However, the journey inward toward the singularity becomes increasingly violent, regardless of the black hole's size. Outside the event horizon, particles and light can still interact with the black hole's immense gravitational field. This interaction creates phenomena such as gravitational lensing, where light from distant stars is bent around the black hole, producing distorted or magnified images. Near the Schwarzschild radius, this bending becomes so extreme that light can orbit the black hole in a perfect circle. This region, known as the photon sphere, lies just outside the event horizon and marks another boundary of strange and fascinating behavior. Singularities, the infinite crunch at the core. At the very heart of a black hole lies the singularity, a place where the normal rules of physics collapse under the weight of overwhelming gravity, while the event horizon marks the boundary where nothing can escape. The singularity represents the black hole's true core, where all the matter it has consumed is crushed into an infinitely small point. When a massive star collapses at the end of its life, its core is compressed to a point where the pressure from its gravity can no longer be balanced by any opposing force. This collapse continues unchecked, squeezing the star's mass into an infinitesimally small space. At the singularity, the density of matter becomes infinite, and spacetime curves infinitely. It is a place where the known laws of physics, particularly those of general relativity, no longer provide clear answers. In most areas of the universe, we can rely on classical physics or general relativity to describe how matter and energy behave. But at the singularity, these rules break down. The concept of infinite density is not something that fits neatly into our understanding of the natural world. It suggests a realm where space-time itself ceases to have meaning, a region where the very fabric of the universe is torn apart. Outside a black hole, gravity acts as a force that pulls objects toward the center of mass. As you get closer to the black hole, this pull becomes stronger and stronger. At the singularity, gravity is no longer just a force. It becomes an overwhelming distortion of space-time. This distortion is so extreme that all matter and energy are funneled into a single point. In the everyday world, time flows forward, and space provides a backdrop for movement. But near the singularity, these concepts blur. Time may stretch infinitely, and space may contract to a point. The exact nature of these changes is unknown, as the equations of general relativity break down under such extreme conditions. To understand the singularity fully, scientists believe a new theory is needed, one that combines general relativity with quantum mechanics. Some researchers hope that a quantum theory of gravity might reveal what happens inside the singularity. Instead of an infinitely small point, the singularity might represent a region where matter is compressed to its smallest possible form, governed by quantum laws. However, such a theory has yet to be developed, leaving the singularity as one of the greatest unsolved mysteries in physics. The equations of general relativity suggest that singularities might exist in other contexts, such as the Big Bang. The early universe, before it began to expand, may have been a singularity, a point of infinite density where space-time was infinitely curved. If this is true, studying the singularities in black holes could provide insights into the origins of the cosmos. Unlike the event horizon, which can be observed indirectly through its effects on nearby matter and light, the singularity is hidden from view. It lies deep within the black hole, concealed by the event horizon. No light or information can escape from this region, making it impossible to study the singularity directly. When something crosses the event horizon, it is pulled inexorably toward the singularity. But what happens to it there? Does it become part of the singularity, adding to its mass and density, or does it undergo some kind of transformation that we cannot yet understand? These questions touch on some of the most fundamental aspects of physics, including the nature of matter, energy, and space-time. The existence of singularities challenges our understanding of the universe in other ways as well. They suggest that there are places in the cosmos where the known laws of physics are incomplete. This has led some scientists to propose that singularities are not physical entities, but mathematical artifacts, features of our equations that point to the need for a deeper theory. Others believe that singularities are real, and that they represent a frontier where new physics will be discovered. Tidal forces. What happens to matter falling in? As matter drifts closer to a black hole, it enters a region where gravity, which feels gentle and consistent on Earth, becomes a relentless force that grows stronger with every passing moment. The closer the matter gets, the more this force varies from one point to another, creating a phenomenon known as tidal forces. These forces are the direct result of gravity's unequal pull across an object. To picture this process, imagine a long object, perhaps a spacecraft or even a human body, falling feet first toward a black hole. Gravity near the black hole isn't uniform. The pull on the feet, which are closer to the black hole, is much stronger than the pull on the head, which is farther away. This difference in gravitational strength stretches the object along its length, pulling the feet downward with greater force, while the head lags slightly behind. The result is a gradual elongation, with the object being stretched thinner and thinner as it falls deeper into the black hole's gravitational field. This stretching force is paired with another effect, compression from the sides. While the object is being stretched vertically, it is also being squeezed horizontally. Gravity acts in all directions, and the curvature of spacetime near the black hole means that the forces from the sides push inward, even as the forces from above and below pull apart. The combination of stretching and squeezing transforms the object into a long, thin strand, resembling a piece of spaghetti, hence the name Spaghettification. For smaller black holes, which have a more compact event horizon, the tidal forces become extreme even before an object crosses the boundary. A person or a spacecraft approaching a stellar mass black hole, for example, would be stretched and torn apart long before reaching the event horizon. The experience would be violent and swift, with the forces ripping apart every molecule of the object in mere moments. In contrast, supermassive black holes, which are millions or even billions of times more massive than the Sun, have much larger event horizons. Near these giants, the tidal forces at the event horizon are relatively mild, because the gravitational gradient is spread out over a much larger distance. An object could theoretically cross the event horizon of a supermassive black hole intact, experiencing little noticeable stretching at first. However, as it continues its journey inward, the tidal forces grow stronger and stronger, and spaghettification becomes inevitable. No matter the size of the black hole, the end result is the same. For matter falling into a black hole, spaghettification is not a sudden event, but a gradual process that unfolds as the object moves closer to the singularity. Imagine a cloud of gas drifting toward a black hole. At first, the gas particles move together as a group, but as they approach the event horizon, the tidal forces begin to take hold. The particles nearest the black hole are pulled ahead, while those farther away lag behind. Over time, the cloud is stretched into a long, thin stream, with individual particles separated by ever-increasing distances. This stream spirals inward, following the curved paths dictated by the warped spacetime around the black hole. Even solid objects, such as asteroids or stars, cannot withstand the immense tidal forces near a black hole. As a star approaches, the outer layers are stripped away first, forming a stream of gas that spirals into the black hole. The core of the star, still held together by its own gravity, may resist the stretching forces for a time, but eventually it too succumbs. The star is shredded into fragments, each of which is stretched and compressed in turn. The process releases enormous amounts of energy, heating the surrounding gas and causing it to emit intense radiation. This is one reason why the regions around black holes are often some of the brightest in the universe, despite the black holes themselves being invisible. From the perspective of an object falling into a black hole, the experience of spaghettification would be profoundly disorienting. Time, already distorted by the black hole's gravity, would seem to slow down. As the object stretches, its perception of space and distance would warp, with the singularity ahead appearing both infinitely far and impossibly close. The forces acting on the object would increase so rapidly that any attempt to resist or counteract them would be futile. The stretching would become so intense that even the atomic structure of the object would break down, reducing it to its fundamental particles. While the idea of spaghettification may seem absurd, it is a real and well-understood consequence of the physics of black holes. The tidal forces responsible for this phenomenon are a direct result of the way gravity interacts with spacetime. In the everyday world, these forces are too weak to notice, but near a black hole, they become powerful enough to shape the fate of anything that ventures too close. By observing how matter behaves as it falls into a black hole, scientists can learn more about the properties of these enigmatic objects and the effects of their intense gravity. Schwarzschild. Black holes, the simplest and most mysterious of them all. Schwarzschild black holes are the simplest kind of black holes. What sets Schwarzschild black holes apart is their lack of rotation and electric charge. They are often considered the starting point for understanding black holes because they strip away all additional complexities, leaving only the bare essentials, mass and gravity. To understand a Schwarzschild black hole, it's helpful to think of it as a perfectly spherical object. Unlike a rotating black hole, which distorts space and creates complex effects like frame dragging, a Schwarzschild black hole is symmetrical in every direction. Its defining feature is its event horizon. The size of this event horizon is determined entirely by the mass of the black hole. This Schwarzschild radius is what gives these black holes their name. A black hole with the mass of the Sun would have a Schwarzschild radius of about 3 kilometers. For contrast, if the Earth were compressed into a black hole, its Schwarzschild radius would be less than a centimeter. This simple relationship between mass and size is one of the reasons Schwarzschild black holes are so important in theoretical physics. They provide a clear and straightforward way to explore the effects of gravity in its most extreme form. One of the key ideas behind Schwarzschild black holes is that they have no hair. This phrase, often used by physicists, means that a Schwarzschild black hole is completely defined by just 3 properties: mass, electric charge, and angular momentum. Since Schwarzschild black holes have no charge or rotation, they are defined solely by their mass. This simplicity makes them a useful model for studying black holes in general. Despite their simplicity, Schwarzschild black holes are far from boring. They provide a clean framework for exploring the fundamental nature of spacetime, gravity, and the limits of human understanding. Because they lack rotation and charge, they allow scientists to isolate the effects of mass and gravity without the complications introduced by other factors. This makes them an essential tool for testing theories of relativity and for developing new ideas about the nature of black holes and the universe as a whole. Schwarzschild black holes also serve as a benchmark for comparing more complex types of black holes. For instance, Kerr black holes, which are rotating, introduce additional phenomena like the dragging of spacetime and the presence of an ergosphere, a region outside the event horizon where objects are forced to rotate with the black hole. Similarly, Reissner-Nordström and Kerr-Newman black holes, which have electric charge, bring even more complexity to the table. By starting with the simplicity of a Schwarzschild black hole, scientists can gradually build up their understanding of these more intricate systems. In space, Schwarzschild black holes are often surrounded by clouds of gas and dust that form an accretion disk. While Schwarzschild black holes themselves do not emit any light, the matter in the accretion disk becomes heated as it spirals inward, emitting intense radiation that can be observed from Earth. This radiation provides indirect evidence of the presence of black holes, even though the black holes themselves remain invisible. In theoretical models, a Schwarzschild black hole can be paired with a hypothetical white hole, which is the opposite of a black hole in that it expels matter rather than pulling it in. Together, they form a structure known as a Schwarzschild wormhole or Einstein-Rosen bridge. Kerr black holes, the rotating monsters of spacetime. Kerr black holes are a different kind of cosmic beast, far more dynamic than their non-rotating Schwarzschild counterparts. Named after the mathematician Roy P. Kerr, who first described them in 1963, these black holes spin at incredible speeds, and their rotation gives rise to some fascinating phenomena. Unlike Schwarzschild black holes, which are static and perfectly symmetrical, Kerr black holes are characterized by their angular momentum, meaning they carry the energy of rotation in addition to their immense gravitational pull. The defining feature of a Kerr black hole is its ability to drag spacetime along with it as it spins. This phenomenon, known as frame dragging, occurs because the rotation of the black hole distorts the fabric of spacetime itself. Imagine placing a heavy ball on a taut rubber sheet and then spinning the ball. The sheet would twist and deform, creating a swirling effect around the ball. In a Kerr black hole, the same thing happens, but on a cosmic scale. The faster the black hole spins, the more pronounced this effect becomes, pulling everything nearby into a swirling motion. One consequence of frame dragging is the creation of an ergosphere, a region outside the event horizon where the effects of the black hole's spin are impossible to escape. The ergosphere is shaped like an oblate spheroid, flattened at the poles and bulging at the equator due to the black hole's rotation. Inside the ergosphere, spacetime is dragged so powerfully that any object within it is forced to move in the direction of the black hole's spin. It's not just a suggestion, it's a law of physics in this extreme environment. Even light, which normally travels in straight lines, is bent and twisted, following the curvature of spacetime. Unlike the event horizon, which represents a true point of no return, the ergosphere allows for a peculiar possibility: energy extraction. Through a process called the Penrose mechanism, particles within the ergosphere can be split into two, with one particle falling into the black hole and the other escaping to infinity with more energy than it originally had. This phenomenon means that Kerr black holes can, in theory, lose rotational energy over time, making them not just cosmic consumers, but also potential sources of energy under the right conditions. Another feature of Kerr black holes is the nature of their singularities. In a Schwarzschild black hole, the singularity is a single point at the center where density becomes infinite and spacetime curvature is at its maximum. In a Kerr black hole, however, the singularity takes the form of a ring, often referred to as a ring singularity. This ring is the result of the black hole's rotation, which stretches and distorts the singularity into a circular shape. The ring singularity lies within the event horizon, but its peculiar geometry opens up theoretical possibilities that are absent in non-rotating black holes. In theory, the ring singularity of a Kerr black hole could serve as a gateway to another region of spacetime, or even to another universe. The extreme conditions near the singularity, including intense gravitational and quantum effects, would likely make such a journey impossible for any real object. But the idea remains a tantalizing aspect of Kerr black hole theory. In a Kerr black hole, the accretion disk rotates in the same direction as the black hole's spin, and the frame dragging effect pulls the inner edges of the disk closer to the event horizon than would be possible in a non-rotating black hole. This allows matter to reach incredible speeds and temperatures, emitting intense radiation that can be observed across vast distances. Kerr black holes are also thought to power some of the most energetic phenomena in the universe, such as relativistic jets. These jets are streams of charged particles that are ejected at nearly the speed of light from the regions near the black hole's poles. While the exact mechanism behind these jets is not fully understood, it is believed that the rotational energy of the Kerr black hole, combined with the magnetic fields in the accretion disk, plays a key role. The result is a pair of powerful beams of energy that can extend for thousands or even millions of light years, influencing the structure and evolution of entire galaxies. For an object falling into a Kerr black hole, the experience would be even more bizarre than in a Schwarzschild black hole. The frame dragging effect would twist the object's trajectory, causing it to spiral inward along a curved path rather than falling straight toward the singularity. Charged black holes, when electromagnetism joins gravity, known as Reissner-Nordstrom black holes, charged black holes, possess an electric charge in addition to their mass. While black holes are most commonly thought of as purely gravitational entities, the presence of charge shows how other fundamental forces of nature can influence their behavior. The inclusion of electromagnetism alongside gravity transforms the dynamics of the black hole, making it unique compared to its uncharged Schwarzschild or spinning Kerr counterparts. The idea of a charged black hole might seem surprising at first. After all, most of the matter that forms black holes, such as stars and gas, tends to be electrically neutral overall. However, in extreme conditions, it is possible for an imbalance between positively charged particles, like protons, and negatively charged particles, like electrons, to develop. If this imbalance becomes significant, the resulting black hole retains an electric charge. The charge is not just a small addition to the black hole's properties, it has profound effects on the spacetime around it. Unlike the simple event horizon of a Schwarzschild black hole, a charged black hole can have two horizons, an outer event horizon and an inner Cauchy horizon. The event horizon functions in much the same way as it does for uncharged black holes, marking the boundary where the escape velocity exceeds the speed of light. The inner Cauchy horizon, however, is a unique feature that arises due to the interplay between gravity and electromagnetism. It acts as a second boundary, closer to the singularity, where the effects of the black hole's charge become more pronounced. In an uncharged black hole, the singularity is a point where density becomes infinite, and spacetime curvature reaches its maximum. In a charged black hole, the singularity is still incredibly dense and extreme, but the electric charge creates a repulsive force that counteracts gravity to some extent. This repulsion does not prevent the formation of the black hole, but it changes the way matter and energy behave as they approach the singularity. For an object falling into a charged black hole, the intense gravitational pull is countered, at least partially, by the electromagnetic force. This repulsion grows stronger as the object gets closer to the singularity, creating a kind of buffer zone where the two forces are in direct competition. Charged black holes also demonstrate a phenomenon known as repulsive gravity. In most situations, gravity is an attractive force, pulling objects toward massive bodies. However, in a charged black hole, the combination of charge and gravity can create regions where the gravitational force is effectively repulsive. This happens because the electric charge produces an outward force that can counteract the inward pull of gravity. The electromagnetic fields surrounding a charged black hole interact with the spacetime curvature caused by the black hole's mass, creating a unique environment where both forces are at play. Charged particles entering this region experience not only the intense gravitational pull of the black hole, but also the effects of the electric and magnetic fields. This dual influence can cause particles to move in spirals or other complex paths, rather than simply falling straight into the black hole. The charge on a black hole represents a kind of potential energy which can be extracted under certain conditions. This idea is similar to the Penrose process in Kerr black holes, where rotational energy can be extracted from the ergosphere. In the case of charged black holes, the electromagnetic fields provide a source of energy that could, in principle, be harnessed. Despite their fascinating properties, charged black holes are thought to be rare in the universe. The reason for this lies in the behavior of charged particles. In most environments, positive and negative charges tend to balance each other out over time. If a black hole were to accumulate a significant charge, it would attract oppositely charged particles, which would neutralize the charge. This natural balancing process makes it unlikely for a black hole to maintain a large electric charge for long periods. However, in certain extreme environments, such as the aftermath of a supernova or within an active galactic nucleus, conditions might allow for the formation of a charged black hole. For objects or particles falling into a charged black hole, the electromagnetic forces near the event horizon would influence their motion, potentially causing them to accelerate or decelerate in unexpected ways. As they approach the inner regions of the black hole, the competition between gravity and the repulsive electromagnetic force would create a unique and turbulent environment. This interplay might even produce observable effects, such as changes in the radiation emitted by matter as it spirals into the black hole. Quasi-black holes, objects that mimic their deadly behavior. Quasi-black holes share some of the same striking characteristics as black holes, such as the ability to trap light or produce intense gravitational effects, but they lack one critical feature, a singularity. Without the infinite density and space-time warping found at the core of a black hole, these objects are not true black holes. Instead, their extreme compactness and mass create conditions that mimic black hole-like behaviors. When an object becomes small enough for its mass, the gravitational pull at its surface increases dramatically. If the object is sufficiently dense, the escape velocity, the speed needed to escape its gravity, can approach or even exceed the speed of light. This is a hallmark of black holes, But quasi-black holes stop just short of crossing the threshold where light is permanently trapped. Instead, light can be temporarily caught in orbits around these objects or delayed in escaping, creating the illusion of a black hole-like shadow. One example of a quasi-black hole is a neutron star, the collapsed core of a massive star left behind after a supernova. Neutron stars are incredibly dense. Just a teaspoon of their material would weigh billions of tons on Earth. This density creates a gravitational pull so strong that it bends the path of light passing near the star. In some cases, the light from the far side of a neutron star is bent back towards an observer, making it possible to see nearly the entire surface of the star at once. This gravitational lensing is a feature shared with black holes, but the neutron star's surface prevents it from becoming a true event horizon. Another example comes from theoretical objects called gravastars, short for gravitational vacuum stars. These hypothetical entities are thought to form when the collapse of a massive star is halted before it can form a singularity. Instead of compressing to infinite density, the matter inside a gravastar could transition into an exotic state, perhaps involving quantum effects or dark energy. The outer shell of the gravastar would be so compact that it would closely resemble the event horizon of a black hole, but without the catastrophic collapse into a singularity. While no gravastars have been observed, their existence remains a topic of theoretical research. Quasi-black holes also include a class of objects known as ultra-compact stars. These stars, which may include hypothetical quark stars or boson stars, represent states of matter even denser than neutron stars. Quark stars, for instance, could form if the pressure inside a collapsing star becomes so great that protons and neutrons break down into their constituent quarks. Boson stars, on the other hand, are purely theoretical and would consist of exotic particles known as bosons. Both types of stars could become dense enough to exhibit behaviors that mimic black holes. The behavior of light near quasi-black holes is striking. In the case of a neutron star, light can become trapped in photon spheres, regions where the gravitational pull is so strong that light rays are forced into circular orbits around the star. Unlike black holes, where light crossing the event horizon is lost forever, the light in a photon sphere can eventually escape if it moves slightly inward or outward. Like black holes, their intense gravity can cause time dilation. For an observer near the surface of a neutron star or ultra-compact star, time would pass more slowly relative to an observer far away. This time, dilation is not as extreme as it would be near the event horizon of a true black hole, but it is still significant. If an astronaut were to orbit close to one of these objects, they might experience hours passing, while days or weeks elapsed for their colleagues far from the star. Another shared feature between quasi-black holes and black holes is their ability to produce jets of high-energy particles. Neutron stars, for instance, can have strong magnetic fields that funnel particles along their magnetic poles. As these particles accelerate to near the speed of light, they produce beams of radiation that can be detected as pulsars if the beams sweep past Earth, while black holes also produce jets. The mechanisms are slightly different, involving the accretion of material and the twisting of magnetic fields near the event horizon. For quasi-black holes, the presence of a solid surface or magnetic field provides the foundation for this phenomenon. Despite their similarities to black holes, quasi-black holes lack the ultimate defining characteristic of true black holes, an event horizon. Without this boundary, there is no point of no return for matter or light. The presence of a physical surface, as in the case of neutron stars, adds layers of interaction that are absent in black holes. For example, matter falling onto a neutron star can collide with its surface, releasing enormous amounts of energy in the form of X-rays or gamma rays. Falling through the horizon, what time feels like inside a black hole. Time behaves strangely around a black hole, but it becomes even more bewildering when you imagine what it would feel like to fall into one. For someone far away, watching you descend toward the event horizon, time seems to slow down for you. Every movement you make, every signal you send, would appear to happen more and more slowly as you approach the boundary. From their perspective, it would seem as if you were frozen in place, hovering just above the event horizon, never quite crossing it. But from your own perspective, things would feel very different. You wouldn't notice anything unusual about time as you approach the event horizon. Your watch would tick normally, and your heartbeat would feel steady. To you, everything would proceed as it always does, even as the universe outside begins to behave in ways that defy intuition. Near the event horizon, spacetime is so heavily curved that the flow of time is significantly distorted. Light, which carries information, struggles to escape the black hole's pull. As light climbs out of this intense gravity well, it loses energy and becomes redshifted, its wavelength stretched to longer and longer lengths. To an outside observer, this makes the signals from someone falling into the black hole appear to slow down and fade away, as if time itself were grinding to a halt. For the person falling, however, there's no sense of this happening. They experience time in their own local frame of reference, where gravity feels constant. The deeper they fall, the stranger their surroundings become, but their personal experience of time remains unaffected by the outside world's distortions. The difference between these two perspectives is a key aspect of relativity. Time isn't a universal constant. It flows differently depending on where you are and how fast you're moving. Once you cross the event horizon, from the perspective of someone watching from afar, you effectively vanish. Any light or signals you emit are trapped by the black hole's gravity, unable to escape and reach the outside world. But for you, the journey continues. The event horizon itself doesn't feel like a physical barrier. You wouldn't notice a sudden change as you crossed it. Inside the event horizon, space-time is so warped that all paths lead toward the singularity at the center of the black hole. This includes paths through both space and time. No matter how hard you try to escape, the geometry of space-time ensures that your future lies at the singularity. It's as if the singularity becomes your destiny, written into the fabric of the universe. The closer you get to the singularity, the more intense the warping of space-time becomes. The tidal forces, which stretch and compress objects near the black hole, also become more extreme. For small black holes, these forces would tear you apart long before you reach the singularity. But for a supermassive black hole, the tidal forces near the event horizon are relatively mild, allowing you to fall much closer to the center before being affected. As you fall deeper, the nature of time itself begins to change. The flow of time is so distorted that it becomes difficult to distinguish between moments. From your perspective, you might feel as though events are speeding up, as if the universe outside the black hole is racing forward in time. This effect, known as gravitational time dilation, occurs because of the immense gravitational pull of the black hole. The deeper you go, the more pronounced it becomes. If you could somehow look back at the universe outside the black hole, you would see time unfolding at an accelerated pace. Stars would appear to age rapidly, galaxies would shift and evolve, and the universe itself might seem to rush toward its ultimate fate. Inside the event horizon, the traditional distinction between past, present, and future begins to break down. The singularity, where space-time curves infinitely, represents a point where the laws of physics as we know them cease to apply. What happens to time and space at this point is one of the great mysteries of modern physics. Some theories suggest that the singularity might connect to other parts of the universe, or even to other universes, creating a kind of bridge through space-time. Others propose that quantum effects could prevent the formation of a true singularity, replacing it with a more complex structure. Time dilation and gravitational redshift. Black holes as cosmic time machines. Imagine an astronaut venturing near a black hole. From their perspective, everything might seem normal. Seconds tick by on their watch, and they continue their work as usual. But for someone watching from a safe distance, the astronaut's movements would seem to slow down, as if they were stuck in a slow-motion video. Even light signals sent back by the astronaut would take longer and longer to reach the observer, stretched out due to gravitational redshift as they climbed away from the black hole's intense gravitational pull. Gravitational redshift affects not just light, but all forms of electromagnetic radiation. Signals sent from near the event horizon would lose energy as they climb out of the black hole's gravity well. This loss of energy stretches the wavelength of the radiation, making it harder and harder to detect. For an outside observer, it would seem as though the signals were slowing down and fading away. This fading of signals creates a kind of optical illusion. To an outside observer, it looks as if objects falling toward the event horizon are frozen in time, stuck forever just above the boundary. In reality, the objects continue to fall, crossing the event horizon and moving toward the singularity. But their light, stretched and redshifted by the black hole's gravity, can no longer escape to reach the outside world. The event horizon acts as a one-way barrier, not just for matter, but for information as well. For the astronaut near the black hole, however, this wouldn't be noticeable. The effects of time dilation and gravitational redshift are relative. They depend on the perspective of the observer. This relativity creates some fascinating possibilities, especially when it comes to the idea of time travel. Time dilation near a black hole is so extreme that it effectively turns the black hole into a kind of natural time machine. Let's say our astronaut spends just a few hours orbiting near the event horizon of a supermassive black hole. When they return to their spaceship, they might find that years or even decades have passed for the crew waiting there. The closer they are to the event horizon, and the longer they stay, the more pronounced this effect becomes. It's a one-way trip forward in time, allowing someone to skip ahead into the future while experiencing only a brief moment themselves. This isn't the kind of time travel we're used to seeing in science fiction. It doesn't allow you to go backward in time or change the past. Instead, it's a natural consequence of the way gravity distorts spacetime. Black holes aren't unique in this respect. Any massive object, including Earth, causes time to pass more slowly near its surface compared to farther away. But the effect is so small on Earth that it's barely noticeable. Near a black hole, the effect becomes overwhelming, creating a true time machine for anyone daring enough to approach. Could we, for example, use the intense gravity of a black hole to leap forward in time, skipping centuries or millennia in the blink of an eye? In theory, this is possible. A spacecraft could orbit close to a supermassive black hole, experiencing time at a fraction of the rate of the universe outside. When the spacecraft returns, it would find that the universe has aged far more than its crew. However, the radiation and tidal forces near a black hole would make it incredibly dangerous, and the energy required to escape its gravity would be enormous. Even if we could solve these problems, there's the question of what it would mean to return to a universe that has moved on without us. The interplay of time dilation and gravitational redshift creates a paradoxical image of black holes. From the outside, they seem like frozen snapshots, holding objects in a timeless state just above the event horizon. But inside, time continues to flow, leading inexorably toward the singularity. This duality reflects the strange and counterintuitive nature of relativity. Inside a Kerr black hole, could you survive the inner Cauchy horizon? Once you cross the event horizon of a Kerr black hole, instead of heading directly toward a singularity, as would happen in a Schwarzschild black hole, you encounter an additional boundary deep within, the Cauchy horizon. This inner horizon is unique to Kerr black holes and represents a region where spacetime begins to behave in ways that challenge our understanding of physics. The existence of the Cauchy horizon is tied to the rotating nature of Kerr black holes and the way they distort spacetime. The Cauchy horizon is not like the event horizon. It doesn't act as a point of no return, but rather as a boundary where predictability vanishes. Beyond this horizon, the equations of general relativity break down. Normally in physics, we rely on knowing the conditions of the present to predict the future. This principle works well in most situations, even under extreme conditions, like those near black holes. But at the Cauchy horizon, this ability to predict what happens next disappears. One reason for this unpredictability is the buildup of energy and information at the Cauchy horizon. As matter and radiation fall into the black hole, they spiral inward and encounter the intense gravitational forces created by the black hole's spin. These forces cause energy to accumulate near the Cauchy horizon, forming what physicists sometimes call a blue sheet. This name refers to the way radiation and particles are compressed and heated to extreme levels as they approach the horizon, creating an environment that could theoretically destroy anything attempting to pass through. If you were an observer falling into a Kerr black hole, your experience of the Cauchy horizon would depend on several factors. In some scenarios, the intense radiation and energy near this boundary would be enough to tear apart any object, no matter how sturdy. This violent interaction makes the idea of survival seem impossible. However, theoretical models suggest that under certain conditions, the destructive effects at the Cauchy horizon might be mitigated. If the black hole has consumed relatively little matter and energy, the buildup near the horizon could be less severe, potentially allowing a brief passage through. What lies beyond the Cauchy horizon is a subject of intense debate and speculation. In theory, Kerr black holes do not have the same type of singularity as Schwarzschild black holes. Instead of a point where density becomes infinite, the singularity in a Kerr black hole is shaped like a ring. This ring singularity, spinning rapidly along with the black hole, creates a unique environment where the rules of spacetime are bent even further. Some theories suggest that passing through the ring singularity could lead to other regions of spacetime, or even entirely different universes. The idea that Kerr black holes might act as gateways to other parts of the cosmos is captivating, though it remains highly speculative. The intense forces at play near the Cauchy horizon and ring singularity make survival seem unlikely, and the physics governing these regions is not fully understood. One of the challenges in studying the Cauchy horizon and other features of Kerr black holes is the lack of direct observational evidence. While we can observe the effects of black holes on their surroundings, the interiors remain hidden from view. Much of what we know comes from mathematical models and simulations, which rely on the principles of general relativity. At the Cauchy horizon, the predictions of general relativity break down, and we need a theory that can incorporate both gravity and quantum mechanics to fully describe what happens. Some researchers argue that the buildup of energy near this horizon could cause it to collapse, effectively destroying the inner structure of the black hole. Others suggest that Kerr black holes could remain stable under certain conditions, allowing the Cauchy horizon and ring singularity to persist. Does space reverse inside a black hole? The role of coordinates. When discussing the peculiar nature of black holes, one of the strangest concepts is the possibility that space and time may exchange roles inside the event horizon. Inside a black hole, the geometry of spacetime behaves so differently from what we experience in everyday life that it defies our usual understanding of direction, movement, and even causality. The role of coordinates becomes central to understanding how this reversal might occur. In the universe as we know it, space and time are interconnected, forming a four-dimensional fabric. Space provides the three familiar dimensions, length, width, and height, while time acts as the fourth dimension, progressing steadily forward. The two are linked by gravity, which bends spacetime in the presence of mass. Around objects like stars and planets, this bending is relatively gentle, but near black holes, the distortion becomes extreme. Outside the event horizon, space and time still behave as expected, although time slows down due to gravitational time dilation. This slowing of time intensifies as you get closer to the black hole's edge. However, once you cross the event horizon, the equations of general relativity suggest a fundamental shift in the nature of spacetime. Inside the event horizon, space and time seem to exchange roles. In the universe outside a black hole, time flows forward and space provides the freedom to move in different directions. But within the event horizon, the curvature of spacetime becomes so extreme that time points toward the singularity at the black hole center. This means that just as you cannot stop moving forward in time outside the black hole, you cannot stop moving toward the singularity once you're inside. It's as if the singularity becomes the inevitable future for anything that crosses the event horizon. Outside a black hole, you can describe a point in spacetime using a set of coordinates, 3 for space and 1 for time. The time coordinate typically measures the progression of events, while the spatial coordinates define a position in three-dimensional space. Inside the event horizon, these roles shift. The radial coordinate, which measures distance from the center of the black hole, begins to act like time, while the time coordinate behaves more like a spatial dimension. This doesn't mean that space and time literally swap places, but rather that their roles in the equations of motion are reversed. Outside the event horizon, you can move in different spatial directions, choosing to approach or move away from the black hole. Time, however, remains constant in its forward progression. Inside the event horizon, the radial direction, movement toward or away from the singularity, becomes fixed, like time. You are drawn inexorably toward the singularity, unable to halt or reverse your motion. The other spatial dimensions remain accessible, but they no longer offer an escape route. The singularity is no longer just a point in space, it becomes your unavoidable future. Outside the black hole, escaping its gravity requires moving outward in the spatial dimension of the radial coordinate. Inside the event horizon, the radial coordinate has become time-like, meaning you cannot reverse your motion in this dimension. Just as you cannot travel backward in time in the universe we know, you cannot travel outward inside a black hole. Our understanding of the universe is shaped by our experience of moving freely through space. Inside a black hole, this familiar framework is turned on its head. The equations describing this reversal come from general relativity, but their implications are difficult to visualize. In other extreme environments, such as near the Big Bang, spacetime could behave in similarly counterintuitive ways. Some theories suggest that the early universe experienced a kind of role reversal between space and time, though on a much larger scale. In our everyday world, we rely on a clear distinction between cause and effect, with time providing the framework for this relationship. Inside the event horizon, where time points inexorably toward the singularity, this distinction becomes less clear. The equations of general relativity suggest that the singularity could act as a boundary where spacetime itself ends, making it impossible to predict what happens beyond it. Black holes challenge our assumptions about space, time, and the fundamental structure of reality. By studying their properties, scientists will uncover new insights into the nature of spacetime and the limits of general relativity. These investigations could eventually lead to a deeper understanding of gravity, quantum mechanics, and the origins of the universe itself. Quantum fluctuations and the strange physics at the singularity. The singularity at the center of a black hole represents a point where the known laws of the universe cease to function in their familiar form. It is in this chaotic region that quantum fluctuations emerge, introducing strange and unpredictable phenomena that challenge our understanding of reality. Quantum fluctuations are tiny, momentary changes in energy that occur in the fabric of spacetime itself. They are a natural feature of quantum mechanics, arising from the uncertainty principle, which states that it is impossible to precisely measure both the position and momentum of a particle at the same time. These fluctuations occur everywhere in the universe, but they are typically too small to have noticeable effects. Near the singularity of a black hole, however, the extreme curvature of spacetime amplifies these quantum effects, making them impossible to ignore. In classical physics, the singularity is often thought of as a final point, a location where spacetime ends and density becomes infinite. But quantum mechanics suggests a more complicated picture. Instead of a single well-defined point, The singularity may be a region filled with violent fluctuating energy fields. These fluctuations could distort spacetime in unpredictable ways, creating temporary microscopic structures that appear and disappear in an instant. Some scientists speculate that these quantum effects might prevent the singularity from ever becoming truly infinite, offering a potential resolution to one of the biggest paradoxes in physics. Some scientists believe that a theory of quantum gravity, which would combine general relativity and quantum mechanics into a single framework, is needed to explain the physics of singularities. Several approaches to quantum gravity have been proposed, including string theory and loop quantum gravity. These theories suggest that spacetime itself may be composed of tiny, discrete units, much like how matter is made up of atoms. If true, this could mean that the singularity is not a point of infinite density, but rather a highly compressed region of spacetime, where these fundamental units interact in complex ways. Quantum fluctuations near the singularity may also give rise to phenomena that defy our usual understanding of cause and effect. In quantum mechanics, particles can sometimes appear to influence each other instantaneously, even when separated by vast distances. This quantum entanglement could play a role in the strange physics near singularities. The intense gravitational forces and warped spacetime might create conditions where entangled particles behave in ways that are difficult to predict or explain using classical physics. One possibility is that quantum fluctuations near a singularity could produce entirely new particles or energy fields. In the chaotic environment of a black hole's core, the immense energy density could trigger processes that are impossible under normal conditions. These processes might include the creation of exotic particles, such as those predicted by theories beyond the standard model of particle physics. In classical physics, time flows continuously and predictably. Near a singularity, however, quantum fluctuations could disrupt the normal progression of time, creating a region where the past, present, and future blur together. Some scientists speculate that time itself might cease to have any meaning at the singularity, replaced by a chaotic and unpredictable sequence of events. Another potential consequence of quantum fluctuations near singularities is the formation of baby universes. Some theories suggest that the extreme conditions inside black holes could create pockets of spacetime that are disconnected from our own universe. These baby universes might expand and evolve independently, forming their own galaxies, stars, and planets. Black holes could be more than just destructive objects. They might also play a role in the creation of new cosmic structures. Despite the theoretical nature of these ideas, they have practical implications for our understanding of the universe. By studying the interplay between quantum mechanics and general relativity near singularities, scientists hope to uncover new insights into the fundamental nature of spacetime. One of the biggest challenges in exploring these questions is the lack of direct observational data. However, scientists are finding innovative ways to study the effects of black holes on their surroundings. Observations of gravitational waves, for example, provide indirect evidence of the extreme conditions near black holes. By analyzing these waves, researchers can test theories about the behavior of spacetime and energy under the most extreme conditions. Einstein-Rosen bridges. Do black holes connect to other universes? Einstein-Rosen bridges, or wormholes, are hypothetical structures that suggest black holes might not simply be destructive endpoints of matter and energy, but could instead act as gateways to other regions of spacetime. Named after Albert Einstein and Nathan Rosen, who first proposed the concept in 1935, wormholes are solutions to Einstein's equations of general relativity that describe a tunnel-like connection between two distant points in the universe, or perhaps even between entirely different universes. At their core, wormholes arise from the mathematical framework of spacetime. General relativity shows that massive objects warp the fabric of spacetime, creating the phenomenon we perceive as gravity. With a black hole, spacetime is so distorted that it essentially forms a pit with no escape. In the Einstein-Rosen model, this pit might extend into a tunnel that connects to another point in spacetime. On paper, the entrance to such a wormhole would resemble a black hole's event horizon, while the other end could appear as either another black hole or a white hole, a theoretical counterpart that expels matter and energy rather than consuming it. Imagine a sheet of paper representing the fabric of the universe. If you fold the paper so that 2 points touch and then punch a hole through them, you've created a visual analogy for a wormhole. Instead of traveling across the surface of the paper, you can take a direct route through the hole, bypassing the distance in between. In theory, this could allow faster-than-light travel across vast cosmic distances, or even provide a means of time travel, depending on how the wormhole is oriented in spacetime. No observational evidence has confirmed their existence, and significant challenges make them difficult to reconcile with the known laws of physics. One major issue is stability. The equations of general relativity suggest that wormholes would be highly unstable, collapsing almost as soon as they form. To remain open long enough for anything to pass through, a wormhole would require an exotic form of matter with negative energy density. This so-called exotic matter has not been observed in nature, though quantum mechanics allows for negative energy in certain situations, such as the Casimir effect. Whether this could ever stabilize a wormhole is an open question. The extreme gravitational forces at the entrances of wormholes would also likely make them impassable for any form of matter. The tidal forces near a black hole's event horizon are already known to spaghettify objects. In the case of a wormhole, these forces could be even more intense, potentially destroying anything attempting to enter. This raises the question of whether wormholes, even if they exist, could ever be used as practical pathways through space-time. Theoretical physicists have explored various types of wormholes, each with its own set of properties and implications. The simplest form is the Schwarzschild wormhole, derived from the same equations that describe non-rotating black holes. However, this type of wormhole is considered purely hypothetical because it requires exotic matter to stabilize and would collapse instantly without it. More complex models, such as Kerr wormholes, arise from rotating black holes and suggest the possibility of more stable structures, though they also rely on exotic matter. Some theories suggest that wormholes could connect not just distant points within our universe, but entirely different universes with their own distinct laws of physics. If true, this would mean that black holes might not simply trap matter and energy forever, but instead transfer them to other regions of spacetime, or even to other universes. If wormholes connect black holes to other regions of spacetime, they could provide a mechanism for information transfer, potentially resolving the black hole information paradox. Some scientists have proposed that wormholes might already exist in the universe, hidden within the vastness of space. If they do, they could be tiny subatomic structures formed during the early moments of the Big Bang. These so-called quantum wormholes would be far too small for humans or even particles to traverse, but could still play a role in the underlying fabric of spacetime. Detecting such wormholes would require advanced technologies capable of observing quantum-scale phenomena, a feat that remains far beyond our current capabilities. Traversable wormholes. Can they exist without collapsing? For a wormhole to be traversable, it must resist the natural tendency to collapse under its own gravity. In most theoretical models, the immense gravitational pull of a wormhole's throat, the narrowest part of the tunnel, would cause it to snap shut almost instantaneously. To counteract this, it would need a stabilizing force, often referred to as exotic matter. Exotic matter isn't just any unusual material. It's a specific kind of substance with negative energy density. This property means that instead of adding to gravitational pull, exotic matter would push outward, holding the wormhole's throat open. In quantum mechanics, certain phenomena suggest the possibility of negative energy. One example is the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience an attractive force due to quantum fluctuations. the energy in the space between the plates is lower than in the surrounding vacuum, effectively creating a region of negative energy. While this phenomenon is measurable, it occurs on a tiny scale and isn't anywhere near the level needed to stabilize a wormhole. Even if exotic matter could be harnessed in large enough quantities, there are other hurdles to making a wormhole traversable. Theoretical models suggest that the distribution of exotic matter would need to be incredibly precise. Too little, and the wormhole collapses. Too much, and the gravitational effects could destabilize the surrounding spacetime. Additionally, the exotic matter would need to remain in place long enough for the wormhole to be useful. In the dynamic environment of the universe, maintaining this delicate balance would be an extraordinary challenge. Even if the throat of the wormhole is stable, the surrounding area would likely be subjected to extreme tidal forces. These forces could tear apart any object attempting to approach the wormhole. To make the wormhole truly traversable, its design would need to account for these forces, either by reducing their intensity or by protecting the traveler from their effects. Some physicists have proposed theoretical models for traversable wormholes that could minimize these challenges. One such model, developed by Kip Thorne and his colleagues in the late 1980s, describes a wormhole stabilized by a thin shell of exotic matter. In this model, the wormhole's throat would be large enough to allow the passage of objects, and the exotic matter would provide the necessary outward pressure to keep it open. Thorne's work was groundbreaking because it showed that traversable wormholes are not forbidden by the laws of physics, at least not in principle. However, these models remain purely theoretical, as we currently lack the means to test or create such structures. If a wormhole connects two distant points in spacetime, and those points experience time differently due to relativistic effects, the wormhole could theoretically be used for time travel. For instance, if one end of the wormhole were placed near a strong gravitational field, or moved at high speeds relative to the other, the time experienced at each end would differ. A traveler passing through the wormhole could emerge at a point in the past or future relative to their starting location. This possibility introduces paradoxes, such as the well-known grandfather paradox, where changes to the past could alter the conditions that allowed the journey in the first place. To address these paradoxes, some scientists suggest that the universe might have mechanisms to prevent them. For example, the concept of chronology protection, proposed by Stephen Hawking, posits that the laws of physics may inherently forbid time travel to the past, perhaps by destabilizing wormholes or creating feedback loops of energy that destroy them. The energy requirements for creating or maintaining a traversable wormhole are another significant obstacle. Calculations suggest that the amount of exotic matter needed would be astronomical, far exceeding anything we could currently produce or manipulate. Some optimistic models propose that quantum effects or advanced technologies could reduce these requirements, but such ideas are far beyond our current reach. If traversable wormholes could exist, they might not only serve as shortcuts through space, but also as gateways to regions of the universe that are otherwise inaccessible. For instance, a wormhole could connect two points separated by billions of light-years, allowing for instantaneous travel across cosmic distances. This could revolutionize our ability to explore the universe, enabling us to study distant galaxies, stars, and planets in unprecedented detail. However, the same properties that make wormholes appealing for exploration also make them potentially dangerous. If a wormhole's stability were to fail while in use, the consequences could be catastrophic for anything inside. Wormholes represent a fusion of imagination and rigorous mathematics, a glimpse into a future where the limits of distance and time might be overcome. Whether they are ever realized or remain confined to the realm of theory, they push us to ask questions about the nature of reality and our place within it. Ring singularities in Kerr black holes, the gateway to elsewhere. Instead of collapsing into a single, infinitely dense point, the intense spin of a Kerr black hole spreads its singularity into a ring. When a massive star collapses into a black hole, it retains the angular momentum it had as a star. This rotation influences the shape and behavior of the black hole, flattening it slightly and causing the singularity to stretch into a thin loop. In theory, the center of this ring is not just a dense core of crushed matter, but a region where spacetime behaves in unusual ways. One of the most intriguing ideas about the ring singularity is that it could serve as a passage to another part of the universe, or even to an entirely different universe. Unlike the crushing finality of a Schwarzschild black hole singularity, the ring singularity of a Kerr black hole may allow spacetime to curve and connect in unexpected ways. This idea stems from the mathematical solutions to Einstein's equations, which suggest that spacetime might not terminate at the ring, but could extend through it. The possibility of a gateway to elsewhere hinges on the concept of spacetime pathways that avoid destruction by the singularity itself. For a Schwarzschild black hole, the intense gravity near the singularity pulls everything into a single point, obliterating all information about the object that fell in. However, in a Kerr black hole, the centrifugal force generated by its spin counteracts some of this inward pull, potentially creating a stable zone within the ring singularity. This stability might allow matter, or even light, to pass through without being crushed. Physicists have explored these ideas through theoretical models, which often suggest that the interior of a Kerr black hole is far more complex than the simple point-of-no-return structure of non-rotating black holes. Some models predict that the ring singularity could act as a wormhole-like structure, linking one part of spacetime to another. Others go further, speculating that it could connect entirely different universes. However, crossing the ring singularity and emerging elsewhere would not be simple. The forces near the singularity are extreme, and any traveler would need to navigate an environment where spacetime is twisted and stretched to its limits. Additionally, the singularity itself might not be stable. If any disturbance, such as the matter falling into the black hole, causes the ring to wobble or collapse, the passage through it could become impassable or even destructive. Near a Kerr black hole, spacetime becomes so warped that the usual rules of time and space begin to blur. Inside the event horizon, regions of spacetime may exist where time flows in loops, creating closed time-like curves. These curves allow for the possibility of time travel. The ring singularity could, in theory, act as an entry point to these strange regions, where the usual flow of time is disrupted. In classical black hole physics, the no-hair theorem suggests that black holes erase almost all details about the matter and energy that fall into them, leaving behind only basic properties like mass, spin, and charge. However, some researchers argue that the unique structure of the ring singularity might preserve certain kinds of information, potentially allowing it to emerge on the other side of the gateway. Many of the ideas about these singularities are based on idealized mathematical models that assume a perfect, symmetrical Kerr black hole. In practice, no black hole is likely to be perfectly symmetrical. The matter and energy falling into a black hole could create instabilities that distort or disrupt the ring's singularity, making it less likely to serve as a reliable gateway. Additionally, quantum effects, which are not fully understood in the context of black holes, could introduce further complications, potentially altering the behavior of the singularity in ways we cannot yet predict. Some scientists also question whether the ring singularity can exist at all. The equations that describe it are based on general relativity, which does not account for the effects of quantum mechanics. Near the singularity, where gravity is at its strongest, quantum effects are likely to play a significant role. A complete theory of quantum gravity, which combines general relativity with quantum mechanics, might just reveal that the ring singularity is an illusion created by the limitations of our current theories. Hyperspace tunnels. Are black holes nature's portals? While they are often described as cosmic traps that consume everything in their vicinity, black holes might also offer a glimpse into higher dimensional realities. Theories about hyperspace tunnels suggest that black holes could serve as gateways, connecting different regions of spacetime, or even providing access to dimensions beyond the four we experience daily. The singularity at the center of a black hole represents a point where the curvature of spacetime becomes infinite and conventional physics breaks down. However, in some interpretations of these equations, this intense curvature might also create shortcuts or pathways to other parts of the universe or to other universes altogether. The concept of hyperspace is not new. In theoretical physics, hyperspace refers to a realm of higher dimensions that go beyond the familiar three dimensions of space and one of time. These extra dimensions are a central feature of string theory, which posits that the fundamental particles of the universe are tiny vibrating strings existing in a multidimensional space. In such a framework, black holes might act as natural openings into this hyperspace, offering a way to traverse vast cosmic distances or explore regions of reality that lie hidden from our perception. If black holes are gateways to other dimensions, what lies on the other side? Could they lead to parallel universes where the laws of physics are different from our own? Or might they serve as shortcuts within our own universe, providing a way to travel through time as well as space? One intriguing idea is that black holes might act as cosmic recycling centers, pulling in matter and energy from one part of the universe and ejecting it into another. This concept is supported by the idea of white holes. While black holes pull matter in, white holes would push it out, potentially creating a flow of energy and information between different regions of spacetime. Some theories even suggest that our universe could have been born from a white hole, emerging as the other side of a black hole in a parent universe. Despite the allure of these ideas, the scientific evidence for hyperspace tunnels and black hole portals remains purely theoretical. Observing such phenomena directly is incredibly challenging, as black holes themselves are hidden behind their event horizons. Some of the most promising research in this area comes from the study of quantum gravity. In a quantum framework, the singularity at the center of a black hole might not be a point of infinite density, but rather a region where spacetime is highly curved and fluctuating. These quantum fluctuations could create pathways through hyperspace, offering a glimpse into the deeper structure of reality. If advanced civilizations exist elsewhere in the universe, they might have discovered ways to harness this power of black holes for travel. This raises the question of whether some of the mysterious phenomena we observe in space, such as bursts of gamma rays or unusual patterns of radiation, could be evidence of alien activity near black holes. While there is no direct evidence to support this idea, it adds another layer of intrigue to the study of these enigmatic objects. The white hole hypothesis. What lies on the other side? If black holes are known for pulling matter and energy in, white holes represent their theoretical opposite, ejecting matter and energy instead of consuming it. Though no direct evidence of white holes has been observed, the mathematical foundations for their existence emerge naturally from the same equations that describe black holes. They raise questions about the nature of spacetime and the ultimate fate of matter caught in the gravitational grip of a black hole. White holes first appeared as a solution to Einstein's equations of general relativity. These equations describe how massive objects curve spacetime, and they allow for a theoretical construct that behaves in reverse to a black hole. In the simplest terms, while nothing can escape from a black hole once it crosses the event horizon, nothing can enter a white hole from the outside. Instead, white holes are thought to continuously emit matter and energy into the surrounding universe. This property makes them a mirror image of black holes, creating a curious symmetry in the mathematics of spacetime. In a black hole, time for an infalling observer appears to slow down dramatically as they approach the event horizon, eventually seeming to freeze at the singularity. A white hole reverses this dynamic, with time seemingly running backward for matter being ejected. This means that a white hole could theoretically be seen as the rewinding of a black hole's processes, expelling everything that the black hole had previously consumed. If white holes exist, they could offer an explanation for some of the more mysterious phenomena observed in the universe. The immense bursts of energy known as gamma-ray bursts, which are among the most powerful explosions in the cosmos, might originate from white holes. These bursts are currently attributed to events like the collapse of massive stars or the collision of neutron stars, but the idea that some could also come from white holes adds an intriguing possibility to the list of explanations. One of the most interesting aspects of the white hole hypothesis is its connection to the idea of black hole recycling. In this framework, matter and energy consumed by a black hole are not lost forever, but are instead funneled through a white hole, emerging in another part of the universe, or perhaps even in another universe entirely. This connection is closely tied to the concept of wormholes, which could link a black hole and a white hole. In this scenario, the black hole acts as the entrance to the wormhole, while the white hole serves as the exit. However, for a wormhole to remain stable, it would require the presence of exotic matter. Without this exotic matter, any connection between a black hole and a white hole would be purely theoretical, existing only in the mathematical models of general relativity. Some physicists have speculated that the Big Bang might have been a kind of white hole. In this scenario, all the matter and energy that now make up the universe were expelled from a white hole in a massive outpouring, creating the cosmos as we know it. While this idea is far from proven, it offers an intriguing perspective on the relationship between black holes, white holes, and the nature of space-time. Despite their theoretical elegance, white holes face significant challenges when it comes to fitting into our current understanding of physics. One of the primary issues is their apparent instability. Unlike black holes, which can persist for billions of years, white holes would likely be highly unstable due to the immense amount of energy they emit. Any small disturbance in the surrounding environment could cause a white hole to collapse, making them fleeting and difficult to detect. Another challenge lies in the second law of thermodynamics, which states that the entropy of a closed system can only increase over time. Black holes are consistent with this law, as they increase in entropy as they consume matter. White holes, on the other hand, appear to violate this principle by ejecting matter in an organized fashion, seemingly reducing entropy. Reconciling this apparent contradiction would require a deeper understanding of the relationship between black holes, white holes, and the arrow of time. Despite these challenges, the study of white holes continues to inspire theoretical research and debate. One compelling idea is that white holes might exist not in isolation, but as part of a larger cosmic network. In this view, the universe could be filled with interconnected black holes and white holes, forming a kind of cosmic recycling system where matter and energy flow between different regions of space-time. This network could help explain some of the large-scale structures observed in the universe, such as the distribution of galaxies and the patterns of cosmic radiation. White holes challenge our understanding of causality. In the strange environment of a white hole, the flow of time and the sequence of events could behave in ways that defy our everyday intuition. This raises profound questions about the nature of time itself, and whether the universe operates according to a single, unified timeline or a more complex, multi-dimensional framework. Naked singularities. Can singularities ever be exposed? Typically, singularities are hidden behind event horizons, ensuring that the chaos within remains out of reach and invisible to the rest of the universe. This protective veil, known as the cosmic censorship conjecture, suggests that nature prevents singularities from being directly observed. However, the concept of a naked singularity, one not cloaked by an event horizon, is an intriguing possibility worth considering. If a singularity were to exist without the event horizon's protective boundary, its extreme gravitational effects could, in theory, ripple outward, affecting its surroundings in unpredictable ways. This scenario defies the cosmic censorship conjecture, which posits that the universe somehow enforces a rule to keep singularities hidden. The question of whether naked singularities can exist arises naturally in certain mathematical solutions to Einstein's equations of general relativity. These solutions describe how matter and energy warp spacetime, and under specific conditions, they suggest that singularities could form without an accompanying event horizon. One example is in the collapse of massive stars. If a collapsing star's angular momentum or spin is high enough, or if it possesses a strong electric charge, the equations predict that an event horizon might not fully form. Instead, the singularity could remain exposed, visible to the rest of the universe. In extreme cases, where the spin of the black hole approaches a critical limit, the mathematics suggest that the event horizon could vanish, leaving the singularity bare. Similarly, Reisner-Nordstrom black holes, which are electrically charged, might also shed their event horizons under certain conditions. These scenarios highlight how extreme environments in the universe might push the boundaries of what is physically possible. Without the shielding effect of an event horizon, the singularity's intense gravitational field would be free to interact with its surroundings. This could create distortions in spacetime that propagate outward, potentially altering the trajectories of nearby objects or producing unusual gravitational waves. The effects of a naked singularity could even extend to the behavior of light, bending and warping it in ways that might allow astronomers to identify these elusive objects. Because the laws of classical physics break down at singularities, observing one directly could provide a unique opportunity to study the fundamental forces of nature under conditions of extreme curvature and density. Quantum gravity might find its first experimental test in the behavior of a naked singularity. This makes the search for evidence of these objects a compelling area of research for physicists. Despite the tantalizing possibilities, the existence of naked singularities remains unproven, and many scientists are skeptical. The cosmic censorship conjecture, proposed by physicist Roger Penrose in the 1960s, has become a cornerstone of general relativity. It asserts that the universe abhors naked singularities, ensuring that they are always hidden by event horizons. This conjecture has not been rigorously proven, but it aligns with the observed stability and predictability of the cosmos. Without the censorship of event horizons, the equations of general relativity could produce chaotic and unpredictable outcomes, undermining the consistency of the physical laws that govern the universe. Testing the cosmic censorship conjecture is challenging, as it requires detailed knowledge of the dynamics of black hole formation and collapse. Computer simulations of stellar collapse have provided some insights, suggesting that event horizons usually form to enclose singularities. However, these simulations rely on approximations and assumptions that might not capture the full complexity of real-world physics. Some studies have even produced scenarios where naked singularities briefly emerge before being reabsorbed into a black hole or dissipating entirely. These transient events hint at the possibility that naked singularities could exist under specific conditions, even if they are rare and short-lived. Observations of high-energy phenomena or unusual gravitational lensing patterns might offer indirect clues. If a naked singularity were to influence the motion of nearby stars or emit unique radiation signatures, these effects could be detectable with current or future instruments. However, distinguishing these signals from those of other cosmic objects, like black holes or neutron stars, is challenging. If singularities can exist without event horizons, they might represent a new class of cosmic objects, one that bridges the gap between black holes and other compact entities like neutron stars. This could reshape our understanding of how matter behaves under extreme conditions, as well as the ultimate fate of collapsing stars. Advances in observational technology might eventually provide the tools needed to detect these elusive objects. In the meantime, physicists continue to explore their properties through theoretical studies and computer simulations, probing the boundaries of general relativity and the mysteries of spacetime. Black hole entropy, the hidden information on the horizon. At its core, entropy is a measure of disorder or the number of possible arrangements of a system's components. In classical physics, black holes were once thought to be simple objects, defined only by their mass, charge, and spin. But the introduction of entropy into black hole physics changed this perspective, revealing a hidden layer of complexity. The idea of black hole entropy emerged from a question that challenged the second law of thermodynamics. This law states that the total entropy of a closed system can never decrease. In other words, disorder in the universe must always increase, or at the very least, remain constant. Imagine a scenario where matter, rich in entropy, falls into a black hole. If black holes were truly simple and featureless, as once believed, it would seem that the entropy carried by the matter would vanish, violating the second law. This apparent paradox led physicists to reconsider the nature of black holes. Jacob Bekenstein, in the early 1970s, proposed a bold solution. He suggested that black holes must have entropy, and this entropy should be proportional to the surface area of their event horizon, not their volume. This was a radical departure from the way entropy is typically understood in everyday systems, where it scales with the volume of a system. For black holes, the event horizon, the boundary beyond which nothing can escape, acts as the defining surface. Bekenstein's insight tied the entropy of a black hole to its geometry, suggesting that the horizon held the key to understanding its hidden information. Shortly after Bekenstein's proposal, Stephen Hawking made a groundbreaking discovery. By applying quantum mechanics to black holes, he showed that they are not entirely black. Instead, they emit a faint radiation, now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where particle-antiparticle pairs are created. One of these particles escapes into space, while the other falls into the black hole, making it appear as though the black hole is emitting energy. Over immense timescales, this process causes the black hole to lose mass and eventually evaporate. Hawking's discovery was significant because it connected black holes to thermodynamics in a profound way. If black holes emit radiation, they must have a temperature. And if they have a temperature, they must also have entropy. The entropy of a black hole, as calculated by Hawking, is proportional to the surface area of its event horizon, with a constant factor involving the Planck length, a fundamental unit in quantum physics. This result not only confirmed Bekenstein's hypothesis, but also provided a concrete formula for black hole entropy. In classical physics, information about a system, such as the position and velocity of particles, is preserved over time. This principle, known as determinism, is central to our understanding of how the universe operates. However, black holes challenge this idea. When matter falls into a black hole, its information seems to disappear behind the event horizon, becoming inaccessible to the outside world. This creates what is known as the information paradox. The information paradox raises a fundamental question. Is the information truly lost, or is it somehow preserved in a way we don't yet understand? If the information is lost, it would mean that the laws of quantum mechanics, which require information to be conserved, are violated. This would be a profound break from the principles that govern much of modern physics. On the other hand, if the information is preserved, it raises the question of where it resides and how it can be recovered. One intriguing possibility is that the information is encoded on the event horizon itself. This idea is supported by the holographic principle, a concept in theoretical physics that suggests all the information contained in a three-dimensional region of space can be represented on a two-dimensional surface. In the case of a black hole, the event horizon acts as this surface, storing information about everything that has fallen into the black hole. The holographic principle was inspired in part by the work on black hole entropy. If the entropy of a black hole is proportional to the area of its event horizon, rather than its volume, it implies that the horizon has a capacity to store information. This leads to the startling conclusion that the universe itself might operate like a hologram, with the three-dimensional world we experience being a projection of information encoded on a two-dimensional surface. One of the biggest challenges is reconciling the thermodynamic description of black holes with the underlying quantum mechanics. Hawking radiation, for instance, appears to carry no information about the matter that fell into the black hole, which seems to support the idea that information is lost. However, some theories suggest that subtle correlations in the radiation could encode this information, allowing it to escape over time. Another possibility is that the information is not lost, but rather stored in a highly scrambled form. In this view, the event horizon acts like a cosmic hard drive, recording information in a way that is incredibly difficult to decipher. This idea aligns with the notion of entropy as a measure of disorder. The information is still present, but it is so thoroughly mixed that it appears to be gone. Unraveling this hidden information would require a deep understanding of the quantum properties of spacetime. Some models suggest that spacetime itself emerges from the quantum entanglement of information stored on surfaces like the event horizon. In this view, black holes are not just exotic objects, but essential components of the fabric of reality, providing a window into the interplay between quantum mechanics and gravity. The study of black hole entropy has also inspired practical advances in physics, particularly in the field of quantum information theory. By exploring how information is stored, transferred, and scrambled in black holes, scientists have developed new tools for understanding quantum systems more broadly. These tools have applications in fields ranging from cryptography to the development of quantum computers. The firewall paradox. Are black holes encircled by walls of fire? The idea of a black hole's event horizon being surrounded by a blazing wall of energy, often called a firewall, arose from efforts to resolve the long-standing information paradox. The paradox touches on the core principles of quantum mechanics and general relativity, and the firewall hypothesis emerged as a potential, albeit unsettling, solution. According to Einstein's theory of general relativity, the event horizon of a black hole is a smooth, invisible boundary. If you were to fall toward a black hole, you wouldn't notice anything unusual as you crossed this boundary. For an observer outside the black hole, time would appear to slow down for you as you approach the horizon, but from your perspective, the crossing would feel unremarkable. This seamless transition is a cornerstone of general relativity, which insists that the laws of physics remain the same everywhere in spacetime, including at the event horizon. In the 70s, Stephen Hawking demonstrated that black holes emit Hawking. Over time, this radiation causes a black hole to lose mass and eventually evaporate, with information being erased, violating principles of quantum mechanics that information must always be conserved. In 2012, a group of physicists proposed a radical solution. They suggested that the smooth event horizon predicted by relativity might not be smooth at all. Instead, it could be a highly energetic region, a firewall, where quantum effects create intense radiation. If this is true, any object falling toward the black hole would encounter this firewall and be instantly incinerated before it could cross the event horizon. The firewall hypothesis is based on a logical inconsistency between three key principles: the conservation of information, the equivalence principle, and the idea that Hawking radiation is completely random. The equivalence principle, a cornerstone of general relativity, states that an observer falling freely into a black hole should experience no dramatic changes at the event horizon. But if information must be preserved, as quantum mechanics demands, then something unusual must happen at the horizon to prevent the loss of information. The firewall hypothesis resolves this by essentially sacrificing the equivalence principle. It proposes that the event horizon is not a benign boundary, but a searing barrier where intense radiation burns up any incoming matter. The idea of a firewall suggests that the smooth spacetime predicted by relativity might break down at the event horizon, creating a violent, chaotic region instead. This goes against the intuitive idea that black holes are relatively simple objects, defined only by their mass, spin, and charge. If firewalls exist, they would represent a dramatic departure from the elegant simplicity of Einstein's equations. Under the traditional view of relativity, crossing the event horizon is an uneventful process. An astronaut falling toward a black hole would notice nothing unusual at the horizon, though they would eventually be stretched and torn apart by tidal forces as they approach the singularity. But if firewalls exist, this serene picture is replaced by a far more violent scenario. Instead of crossing the horizon smoothly, the astronaut would be vaporized by the intense radiation of the firewall, leaving no trace behind. Many find the idea of firewalls unpalatable because it violates the equivalence principle, a cornerstone of general relativity. The principle has been tested extensively and is considered one of the most reliable aspects of Einstein's theory. Sacrificing it to resolve the information paradox feels like a drastic step, and some physicists argue that there must be another solution. Several alternative ideas have been proposed to address the paradox without invoking firewalls. One possibility is that the information about what falls into a black hole is encoded in the Hawking radiation itself. This would mean that the radiation is not entirely random, but carries subtle correlations that preserve the information. If this is true, then the smooth event horizon predicted by relativity could remain intact, and the need for a firewall would disappear. Another possibility is that the information is stored on the event horizon in a highly scrambled form, as suggested by the holographic principle. This idea proposes that the event horizon acts like a two-dimensional surface where all the information about the black hole is encoded. If this is true, then the information is not lost, but is simply hidden from view, preserving both quantum mechanics and the equivalence principle. But if firewalls really do exist, they would suggest that spacetime is not as smooth and continuous as Einstein envisioned. Instead, it might be a highly dynamic quantum structure that becomes chaotic under extreme conditions. This would have profound implications for our understanding of the universe, suggesting that spacetime is far more complex than it appears on the surface. Quantum tunneling into a black hole. Could particles escape after all? Quantum tunneling describes the ability of particles to pass through barriers that, according to classical physics, should be impenetrable. At the subatomic level, particles like electrons do not behave like tiny solid balls. Instead, they act more like waves. These waves, representing the probability of where a particle might be, can extend into regions that classical physics would define as off-limits. This allows a particle to occasionally tunnel through a barrier, effectively appearing on the other side without crossing it in the usual sense. The event horizon of a black hole is often thought of as a one-way surface. Anything crossing it is believed to be irreversibly trapped. But at the quantum level, the rules of physics are different. Particles are not constrained by the same strict boundaries that apply in the macroscopic world. The wave-like nature of particles means that their probability distributions extend beyond the event horizon, raising the possibility of tunneling. Stephen Hawking proposed that pairs of virtual particles constantly pop into existence near the event horizon due to quantum fluctuations. Normally, these pairs annihilate each other almost immediately. But if one of the particles falls into the black hole while the other escapes, the escaping particle becomes real and contributes to what we observe as Hawking radiation. Over time, this process causes the black hole to lose mass and eventually evaporate. Hawking radiation is a form of quantum tunneling, as the escaping particles must borrow energy to overcome the gravitational pull of the black hole. Hawking radiation involves particles forming just outside the event horizon. The idea of tunneling from within the black hole is more challenging. The event horizon represents a point of no return, where the escape velocity exceeds the speed of light. For a particle inside this boundary, escaping would require it to exceed this speed, which is impossible according to relativity. However, quantum tunneling does not obey the same rules as classical motion. It relies on the probabilistic nature of quantum mechanics, where particles have a non-zero chance of appearing on the other side of a barrier, even if that barrier seems insurmountable. The probability of tunneling depends on the properties of the barrier, such as its width and height. In the case of a black hole, the event horizon can be thought of as an infinitely high barrier. This would suggest that the probability of tunneling out is extremely small, but not necessarily zero. If tunneling were possible, the process would likely be extraordinarily rare, happening over timescales far longer than the age of the universe. Even so, the theoretical possibility challenges our understanding of black holes as completely inescapable prisons. It would mean that black holes are not entirely closed systems. Information or matter could potentially escape, albeit in a highly degraded form. If tunneling allows particles to escape, it could provide a mechanism for some information to be recovered, even if it is incomplete or distorted. The singularity is a point where density becomes infinite. But quantum mechanics might offer a way to bypass the singularity entirely. If particles could tunnel away from the singularity and escape the black hole, it would suggest that the singularity is not an absolute endpoint, but rather a region where quantum effects dominate. Some theories in quantum gravity suggest that spacetime near the singularity might be fundamentally different from what we experience in the rest of the universe. Instead of being smooth and continuous, spacetime could be granular or foamy at the smallest scales. This granularity might allow particles to exploit tiny fluctuations in spacetime, enabling them to tunnel through the intense gravitational field of the black hole. If this is true, it could provide a pathway for particles to escape. The study of quantum tunneling in the context of black holes is still highly theoretical. It relies on uniting general relativity with quantum mechanics. These two frameworks are not yet fully compatible, and physicists are still working toward a theory of quantum gravity. Until such a theory is developed, the idea of tunneling from inside a black hole remains speculative. If particles really can escape through tunneling, it could mean that black holes are constantly interacting with their surroundings in subtle ways, even as they seem to consume everything that comes near them. This would make black holes not just cosmic sinks, but also sources of information and energy, playing a more dynamic role in the universe. If particles can escape through tunneling, it could also accelerate the process of black hole evaporation. Over vast timescales, this might lead to the complete disappearance of black holes, leaving behind only faint traces of their existence. This would have profound implications for the evolution of the universe, as black holes are thought to play a key role in shaping galaxies and influencing the distribution of matter. Planck stars, a quantum explanation for the singular core. The idea of Planck stars comes from a theory called loop quantum gravity. In loop quantum gravity, spacetime itself is not continuous but is instead made up of tiny discrete units, much like a fabric woven from individual threads. These units are incredibly small, on the order of the Planck length, which is about 1.6 times 10 to the power of negative 35 meters. At this scale, the smooth curves of spacetime described by Einstein's equations are replaced by a granular structure. This granular nature could fundamentally change how black holes behave at their cores. When matter collapses into a black hole, classical physics predicts that it will be compressed indefinitely, forming a singularity. However, loop quantum gravity suggests that there is a limit to how much matter can be compressed. This limit is reached when the density of the collapsing matter approaches the Planck density, which is unimaginably high, about 5.1 times 10 to the power of 96 kilograms per cubic meter. At this point, quantum effects come into play, preventing the formation of a true singularity. Instead of collapsing indefinitely, the matter rebounds, forming what is known as a Planck star. A Planck star is not a star in the traditional sense. It does not emit light or heat in the way that ordinary stars do. Instead, it is an incredibly compact and dense object that exists within the event horizon of a black hole. To an outside observer, the Planck star would be hidden from view, as the event horizon prevents any light or information from escaping. However, the existence of a Planck star changes the story of what happens inside a black hole. It replaces the infinite density of a singularity with a finite, calculable structure, offering a way to describe black holes without the troubling infinities. Just as electrons in atoms are prevented from collapsing into the nucleus by quantum mechanics, the matter in a black hole could be prevented from collapsing into a singularity by similar quantum effects. This quantum pressure arises from the granular structure of spacetime itself, which resists further compression. In this view, a Planck star represents a balance between the inward pull of gravity and the outward push of quantum pressure. In classical physics, black holes are thought to persist indefinitely, slowly evaporating through Hawking radiation over immense timescales. However, if the core of a black hole is a Planck star, this process might unfold differently. The extreme density of the Planck star could cause it to radiate energy in ways that are not yet fully understood. Over time, this radiation could lead to the black hole's complete evaporation, leaving behind no singularity, but instead a faint remnant of its quantum structure. One intriguing aspect of Planck stars is their potential connection to the black hole information paradox. If a black hole's core is a Planck star, it might provide a way to preserve this information. The granular structure of the Planck star could act as a kind of memory, storing information about the matter that formed it. As the black hole evaporates, this information might be released back into the universe, resolving the paradox. In classical physics, time and space become distorted near the singularity, with time effectively stopping at the event horizon. However, the quantum effects that create a Planck star could alter this picture. Instead of time stopping, it might continue to flow in strange and unpredictable ways, governed by the rules of quantum mechanics. It is not yet clear whether loop quantum gravity, the theory that predicts their existence, is the correct description of the universe at the smallest scales. Other theories of quantum gravity, such as string theory, offer different predictions about the nature of black hole cores. However, the concept of Planck stars provides a compelling alternative to the classical idea of singularities, offering a way to reconcile the laws of physics with the extreme conditions inside black holes. If Planck stars exist, they could also have implications for the universe as a whole. Some theories suggest that black holes might play a role in the formation of new universes, with the cores of black holes acting as seeds for cosmic expansion. In this view, a Planck star could represent the starting point of a new universe, where the extreme density of matter and energy triggers a Big Bang-like event. Black hole computers. Could black holes perform quantum computation? Some physicists have speculated that black holes could act as natural quantum computers, processing and storing information. To understand this idea, it's important to think about what makes a black hole unique in terms of information. When matter falls into a black hole, it carries with it properties like mass, charge, spin, and even more complex information. According to classical physics, this information is lost forever. However, quantum mechanics tells us that information cannot simply disappear. Hawking radiation is a result of quantum processes near the event horizon and suggests that black holes slowly lose mass over time. However, Hawking's calculations initially implied that the information about what fell into the black hole is not contained in the radiation. It seems random. Yet, more recent theories propose that the radiation does, in fact, carry traces of the information, though it may be encoded in highly complex ways. This is where the idea of black holes as potential quantum computers begins to emerge. In a quantum computer, information is stored in quantum bits, or qubits, which can exist in multiple states simultaneously thanks to a property called superposition. This allows quantum computers to process vast amounts of information in parallel, solving certain types of problems much faster than classical computers. Black holes, with their ability to store enormous amounts of information on their event horizons, might operate on similar principles. The key lies in the holographic principle. The holographic principle means that the black hole's vast internal complexity could be represented by quantum states on the event horizon. Much like a hologram represents a three-dimensional image on a flat surface. This encoding could theoretically allow the black hole to perform computations on the information it absorbs. Black holes are also incredibly efficient at packing information. The amount of information a black hole can store is proportional to the surface area of its event horizon, not its volume. This means that even a relatively small black hole could store more information than all the computers on Earth combined. The dense storage of information, combined with the quantum processes happening near the event horizon, raises the possibility that black holes could naturally perform calculations as they process the information encoded in the matter and energy they consume. Black holes have an enormous amount of entropy, far exceeding that of any ordinary object. This entropy is closely tied to the black hole's event horizon and plays a central role in theories about how black holes process information. The interplay between entropy and computation suggests that black holes might perform calculations by rearranging the information stored on their event horizons, much like a quantum computer manipulates qubits. When particles are created near the event horizon, their quantum states are influenced by the information stored in the black hole. This could mean that the radiation emitted by the black hole carries out a kind of natural computation, encoding the results in the particles that escape. If this is true, studying Hawking radiation in detail could reveal insights into the computations being performed by the black hole and the information it holds. Some scientists have even speculated that black holes could be used as actual quantum computers, at least in theory. If we could harness the quantum processes happening near a black hole's event horizon, we might be able to perform computations far beyond the capabilities of any man-made device. However, the practical challenges of using a black hole for computation are immense. For one, black holes are incredibly difficult to access and control. Even if we could approach one safely, the extreme gravitational forces near the event horizon would make it nearly impossible to manipulate or retrieve the information being processed. Quantum computers rely on delicate quantum states that are easily disrupted by their environment. Near a black hole, the intense gravitational and quantum effects could make it difficult to maintain the coherence needed for reliable computation. However, some theorists believe that the very properties that make black holes so extreme, like their ability to compress information and their strong gravitational fields, could also help stabilize quantum states, making them ideal for certain types of calculations. Some physicists have suggested that the universe might be a kind of giant quantum computer, with black holes acting as the ultimate processors. In this view, the complex interactions between black holes and the information they absorb could play a role in shaping the structure and evolution of the cosmos. The study of black hole computation is still in its early stages, and many questions remain unanswered. How exactly is information encoded on the event horizon? What kinds of computations could a black hole perform, and how would the results be stored or transmitted? Could black holes be used to solve specific problems, such as factoring large numbers or simulating complex quantum systems? These questions are the subject of ongoing research as physicists work to unravel the mysteries of these fascinating objects. Do black holes seed new universes? The multiverse hypothesis. Some have proposed that black holes might not just be the end of matter and energy, but could serve as the beginning of something entirely new, a separate universe. This idea stems from theories in cosmology and quantum gravity that suggest black holes could act as cosmic wombs, where the collapse of matter within them creates the conditions necessary for a new Big Bang in a separate spacetime. In quantum gravity, singularities may not exist in the way we traditionally think of them. Instead of an infinite density, the collapse of matter might reach a finite but incredibly dense state governed by quantum laws. At this point, some theories propose that the immense energy and compression could create conditions similar to those of the Big Bang, where spacetime itself is born or reshaped. In this sense, the interior of a black hole could act as a kind of seed for a new universe, with its own spacetime fabric branching off from the parent universe. Loop quantum gravity suggests that spacetime is not continuous, but made up of tiny, discrete loops. These loops become incredibly dense near a black hole's core, preventing the formation of a true singularity. Instead, the matter and energy collapse to a minimum volume and then bounce outward, potentially into a new spacetime. This bounce could resemble the birth of a new universe, complete with its own dimensions, physical laws, and constants. The multiverse is the concept that our universe is just one of many, each with its own unique properties. If black holes can create new universes, they might serve as the mechanisms through which the multiverse expands. Each time a black hole forms, the collapsing matter could create a new space-time bubble, disconnected from our own universe. These baby universes might remain forever hidden from us, as their space-time would be separate from ours, but they could grow and evolve just as our universe has. In our universe, information about the physical state of matter and energy is conserved, even as it falls into a black hole. Some scientists speculate that this information could influence the structure and properties of the new universe created by the black hole. For example, the total mass, charge, and angular momentum of the parent black hole might determine the initial conditions of the new universe, including its size, shape, and physical constants. This would mean that each black hole produces a unique universe, shaped by the specific characteristics of the matter that fell into it. Could our universe have been born from a black hole in a parent universe? If so, the properties of our universe, such as the speed of light, the strength of gravity, and the behavior of particles, might reflect the characteristics of the black hole that spawned it. Perhaps the multiverse operates like a vast evolutionary system, with black holes acting as the reproductive mechanism. Universes that produce more black holes would give rise to more offspring universes, potentially shaping the multiverse over time. One challenge to this hypothesis is understanding how the transition from a collapsing black hole to an expanding universe could occur. For a new universe to form, space-time would need to reconfigure itself, breaking free from the constraints of the parent universe. Some theories suggest that this could happen through quantum tunneling. In this case, the event horizon might be the boundary between the collapsing black hole and the emerging spacetime of the new universe. Theoretical physicists have explored mathematical models to describe this process. One such model involves the Einstein-Rosen theory, which extends general relativity by including the effects of spacetime torsion. In this framework, torsion could counteract the infinite compression of matter in a black hole, creating a bounce that initiates the expansion of a new universe. Other models draw on string theory. String theory allows for the existence of extra dimensions, which could play a role in the creation of new universes within black holes. Inside a black hole, the normal flow of time as we experience it ceases to exist. Near the event horizon, time slows dramatically, and at the singularity time as we understand it might effectively stop. In the context of a new universe forming, time could take on an entirely different meaning. The arrow of time in the new universe might point outward from its own Big Bang, just as it does in our universe, creating a separate timeline disconnected from the parent universe. Rather than being mere destroyers of matter and energy, black holes might be creators, driving the cycle of cosmic evolution on a grand scale. What seems like the ultimate collapse could also be a new beginning, hidden from view, but shaping the multiverse in ways we are only beginning to imagine. Dark matter and black holes, are they related or competing theories? Dark matter and black holes each present their own puzzles and challenges to our understanding of cosmology. Both are invisible in a direct sense, black holes because light cannot escape their gravity, and dark matter because it does not emit, absorb, or reflect light. Despite these similarities, they are fundamentally different in what they represent. Black holes are dense objects formed from the collapse of matter, while dark matter is thought to be a diffuse and exotic form of mass that fills the universe. Yet some scientists have proposed intriguing connections between the two, leading to questions about whether dark matter could be made up of black holes, or whether they are entirely separate phenomena. One of the most compelling ideas connecting black holes and dark matter involves primordial black holes. These are hypothetical black holes that might have formed in the early universe shortly after the Big Bang. Unlike the black holes we observe today, which are created from the collapse of massive stars, primordial black holes would have formed from regions of space where matter was densely concentrated. The intense gravitational forces in these regions could have compressed matter into black holes even without the need for stars. If primordial black holes exist, they could range in size from tiny fractions of a millimeter to thousands of times the mass of our Sun. Dark matter is known to account for about 27% of the universe's mass-energy content, far outweighing the visible matter we can see. If primordial black holes are numerous enough, their combined mass could match the observed effects of dark matter, such as the gravitational pull that holds galaxies together and the bending of light around massive objects. Testing this idea has proven difficult. One approach involves looking for the gravitational effects of small black holes passing in front of stars. This phenomenon, known as gravitational microlensing, occurs when a compact object like a black hole bends and magnifies the light from a background star as it moves between the star and Earth. Microlensing surveys have been conducted to search for evidence of primordial black holes, but so far, the results suggest that only a small fraction of dark matter could be made up of black holes in certain size ranges. This does not entirely rule out the possibility, but it indicates that primordial black holes, if they exist, are unlikely to account for all dark matter. Another avenue of investigation is the interaction between black holes and dark matter. While dark matter does not interact with light or ordinary matter in the ways we are familiar with, it does interact gravitationally. This means that dark matter can be influenced by the immense gravitational pull of black holes. In regions of space where dark matter density is high, such as near the centers of galaxies, dark matter might be drawn toward black holes. Once near a black hole, dark matter could form a dense spike around the event horizon, where its gravitational effects might amplify the signals we observe from the black hole, such as the emissions of X-rays or other radiation from infalling matter. Some scientists have speculated that black holes might even consume dark matter, just as they consume ordinary matter. If dark matter is pulled into a black hole, its mass would add to the black hole's total, potentially altering the way the black hole evolves over time. However, since dark matter does not emit light or other forms of radiation when it interacts with a black hole, detecting this process would be extraordinarily challenging. The effects might be indirect, such as changes in the distribution of dark matter around a galaxy, or subtle shifts in the orbits of stars. Certain models of dark matter predict that it could annihilate or decay into detectable particles when compressed to high densities. If this is true, then the regions of space near black holes, where dark matter might be most concentrated, could produce signals that reveal the nature of dark matter. For example, high-energy gamma rays or neutrinos might be emitted as a result of dark matter interactions in the intense gravitational environment near a black hole. Observatories like the Fermi Gamma Ray Space Telescope and IceCube Neutrino Observatory are already searching for such signals, though no definitive evidence has been found so far. If primordial black holes formed in the aftermath of the Big Bang, their distribution and abundance could provide clues about the conditions of the universe at that time. For example, the presence of primordial black holes might explain certain anomalies in the CMB or cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the universe. Additionally, collisions between primordial black holes could produce gravitational waves, ripples in spacetime that can be detected by observatories like LIGO and Virgo. The leading candidates for dark matter are not black holes, but rather particles, such as axions, or weakly interacting massive particles, or WIMPs. These hypothetical particles would interact so weakly with ordinary matter that they are effectively invisible. Yet their collective gravitational effects would account for the missing mass in the universe. Unlike black holes, these particles would not form compact objects or distort spacetime in the same dramatic ways. Instead, they would remain spread out, forming a diffuse halo around galaxies. Even if dark matter is not made up of black holes, the two phenomena might still influence each other in subtle ways. For instance, the presence of dark matter could affect the formation and growth of black holes over cosmic time. In the early universe, regions with higher concentrations of dark matter might have facilitated the collapse of gas and dust into the first stars and black holes. Later, the gravitational pull of dark matter halos around galaxies could have helped funnel material towards supermassive black holes at the centers of galaxies, fueling their growth and activity. Could black holes be the source of dark energy? The accelerated expansion of the universe, first observed in the late 1990s, suggests that galaxies are not only moving away from each other, but doing so at an ever-increasing rate. The force responsible for this acceleration has been termed dark energy, and it is estimated to make up about 68% of the total energy content of the universe. Despite its dominance, scientists know very little about dark energy. It does not interact with light or matter in a way we can directly observe, leaving its nature an enigma. Among the many hypotheses put forward to explain dark energy, one idea is that black holes might play a role in generating or amplifying it. According to quantum mechanics, even the emptiest regions of space are not truly empty. Instead, they are filled with tiny fluctuations where particles and antiparticles momentarily pop in and out of existence. This restless activity is called vacuum energy, and it is thought to permeate all of space. Vacuum energy could be linked to the cosmological constant, a term in Einstein's equations of general relativity that describes a uniform energy density filling the universe. If vacuum energy is indeed the source of dark energy, it would explain the observed acceleration of the universe's expansion. Black holes, with their intense gravitational fields and connection to quantum physics, might have a special relationship with vacuum energy. Near a black hole, spacetime is warped to extreme degrees, creating an environment where quantum effects are amplified. Some researchers speculate that black holes could act as reservoirs or generators of vacuum energy, contributing to the overall dark energy budget of the universe. Black holes grow by accreting matter and merging with other black holes, increasing their mass and size. If black holes are connected to vacuum energy in some way, their growth could lead to an increase in the total amount of dark energy. This hypothesis aligns with observations suggesting that the universe's accelerated expansion began relatively recently, in cosmic terms, roughly 5 billion years ago, coinciding with the period when supermassive black holes in galaxies were actively growing. One particularly bold hypothesis is that black holes themselves could be sources of dark energy. This idea is based on the notion that the energy density inside a black hole might not be confined to the black hole itself, but could have effects on the surrounding spacetime. For example, the intense gravitational pull of a black hole might create a kind of pressure on the vacuum energy in its vicinity, altering its properties and contributing to the overall acceleration of the universe. There are also questions about the role of primordial black holes in the dark energy puzzle. If primordial black holes formed in large numbers shortly after the Big Bang, they could have contributed to the early evolution of the universe in ways we do not yet fully understand. Some theories suggest that these black holes might interact with the vacuum energy of the early universe, influencing its density and distribution. Over billions of years, these interactions could have left an imprint on the universe's expansion, possibly contributing to the dark energy we observe today. Despite these many ideas, there are significant challenges to linking black holes and dark energy. For one, the mechanisms by which black holes could generate or amplify vacuum energy are not well understood and may require new physics beyond our current theories. Additionally, Observations of the CMB radiation and the large-scale structure of the universe place constraints on how dark energy behaves, and it is not clear whether black hole-based models can fully account for these observations. Furthermore, alternative explanations for dark energy, such as modifications to general relativity or the existence of a new field called quintessence, compete with black hole-based hypotheses. New observational tools should provide insights into the behavior of black holes and their potential role in the universe's expansion. For example, studying the distribution and growth of supermassive black holes in galaxies could reveal whether they correlate with changes in the rate of cosmic acceleration. Similarly, detecting subtle effects of vacuum energy near black holes could shed light on the interplay between these two mysterious phenomena. What if we are inside a black hole, the universe as a giant singularity? Some physicists propose that the observable universe might be the interior of a black hole that exists within a much larger parent universe. In this scenario, the Big Bang, which marked the beginning of our universe, could correspond to the formation of a singularity in the parent universe, a moment when matter and energy collapsed into an incredibly dense state. The expansion of our universe, as observed through the redshift of distant galaxies, might be the result of the spacetime inside this black hole stretching and evolving over time. One of the key features of this hypothesis is the idea that the event horizon of this colossal black hole would be so far away that it lies well beyond the observable universe. The observable universe is limited by the speed of light and the finite age of the cosmos, roughly 13.8 billion years. Light from regions beyond this limit has not had enough time to reach us, creating a natural boundary to our observations. If the event horizon of the hypothetical black hole enclosing our universe lies far beyond this boundary, it would be effectively undetectable to us. In a black hole described by general relativity, the curvature of spacetime inside the event horizon is extreme. Space and time themselves are distorted, with space becoming highly compressed and time slowing dramatically near the singularity. In a Kerr black hole, the internal structure is even more complex, with regions where spacetime twists and warps in unexpected ways. These characteristics bear some resemblance to the conditions we observe in our universe, such as the uniform expansion of spacetime and the stretching of time due to gravity. Cosmologists often describe the universe as being homogeneous and isotropic on large scales, meaning it looks roughly the same in all directions and locations. This large-scale uniformity could be consistent with the interior of a black hole, where the distribution of matter and energy is influenced by the extreme curvature of spacetime. Additionally, the CMB could be interpreted as a relic of the initial collapse of matter into the singularity. Black holes have entropy which is proportional to the surface area of their event horizon. Similarly, the universe as a whole appears to have entropy, and its thermodynamic behavior is described by the laws of cosmology. If the universe is indeed the interior of a black hole, the event horizon of this black hole might encode all the information about the contents of our universe, consistent with the holographic principle. The rapid inflationary period following the Big Bang, during which the universe expanded exponentially, might be analogous to the extreme warping of spacetime near a black hole's singularity. But how did the singularity at the heart of this hypothetical black hole give rise to the complexity and structure we observe in the universe today? In traditional black hole physics, the event horizon acts as a one-way boundary, preventing anything from escaping the black hole's gravitational grip. If our universe is inside a black hole, it is unclear whether any interaction with the parent universe is possible, or whether our universe is completely self-contained. The black hole. Multiverse. How many universes could exist beyond? Each black hole in our universe, of which there are likely billions or even trillions, could give rise to its own universe. And if those universes also contain black holes, the process could repeat, leading to an ever-branching multiverse. This infinite nesting of universes raises profound questions about the nature of reality and whether there is a fundamental parent universe that started it all, or if the process has been ongoing forever. In our universe, the strength of gravity, the speed of light, and the properties of fundamental particles are all determined by specific constants. These constants govern everything, from the formation of stars to the behavior of atoms. But there is no reason to assume that these constants would remain the same in a universe spawned by a black hole. The conditions at the moment of creation, inside the black hole, could influence the values of these constants, resulting in universes that are vastly different from our own. Some universes might have stronger gravity, causing stars to burn out quickly or collapse into black holes almost immediately. Others might have weaker gravity, making it difficult for galaxies to form at all. There could be universes where light travels at different speeds, where time flows differently, or where the basic building blocks of matter are unrecognizable. Some of these universes might be teeming with life, while others could be barren or even entirely inhospitable to any form of complexity. If black holes give rise to new universes, and if the properties of those universes are influenced by the conditions inside the black hole, then certain types of universes might be more likely to produce black holes themselves. In this scenario, universes that are good at creating black holes might become more common over time, leading to a kind of natural selection. This idea, known as the cosmological natural selection hypothesis, suggests that our universe might be particularly good at creating black holes because its physical laws favor their formation. If black holes are gateways to new universes, is it possible to travel between them? The intense gravitational forces near the event horizon likely destroy anything attempting to enter. Even if one could survive, the conditions inside the black hole are so extreme that they defy our current understanding of physics. Additionally, the singularity at the center of the black hole represents a point where spacetime itself breaks down, making it unclear how it might connect to another universe. Despite these obstacles, the multiverse hypothesis remains a tantalizing possibility. It provides a potential answer to some of the biggest questions in cosmology, such as the origin of the universe and the nature of the Big Bang. If our universe was born from a black hole in another realm, it suggests that the cycle of creation and destruction is a fundamental feature of the cosmos. Each universe, in this view, is both a product of the past and a seed for the future. In a multiverse filled with countless universes, each with its own unique properties, our universe might seem like just one small part of a much larger whole. Yet this perspective can also be humbling and inspiring. It suggests that the cosmos is far more complex and varied than we can currently comprehend, with endless possibilities waiting to be explored. But this is where we end our own exploration. Were there any wacky ideas that we missed? What would you like us to cover next? Send us your ideas in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.